Hello everyone. Today we'll be discussing quantum theory of light and photoelectric effect. To understand this, we need to understand what are wave motion. Um, we know that waves propagate through different mediums. And, suppose if this is the mean position, the wave propagates this way. The maximum displacement from the mean position to the top is called the amplitude of the wave, and the distance between two crests or two troughs is the wavelength. It's denoted by lambda, and the units we express in terms of nanometers. And the number of cycles that, or number of wavelengths that passes through a point at a given time is called the frequency of the wave, and it's denoted by nu, and the unit is in terms of hertz or per second. And we have another term called the wave number, and it's nothing but 1 over lambda, and this is denoted by nu bar. Sorry, this is lambda. And relationship between speed of light c, wavelength, and nu is this. This is an important relation. And we'll move on to electromagnetic wave radiation. Electromagnetic wave radiation. Now, in 1870, James Clerk Maxwell proposed that light and other forms of radiant energy propagates through space and in turn are associated with magnetic fields, and hence they are called as electromagnetic waves. When light passes through, light also travels in the form of a wave. So suppose the light is traveling as a wave, but what Maxwell is suggesting is that magnetic fields are also traveling perpendicular to the wave, so perpendicular to the light waves, and they travel together, they go hand in hand. So light waves are also called, they are associated with electric and magnetic field, therefore they are called electromagnetic waves. Different types of radiation exhibit this type of electromagnetic waves or electromagnetic nature. Now we know that the visible light can be split into seven different colors, and each color is associated with a different frequency or wavelength. Likewise, different types of radiation or different types of energy, electromagnetic radiations, are classified or are put together in what we call the electromagnetic spectrum. Electromagnetic spectrum. This electromagnetic spectrum is an arrangement of different waves in terms of increasing order of wavelength or decreasing frequency. Because once you increase the wavelength, the number of cycles passing through a point will eventually decrease, so the frequency decreases. Now, the electromagnetic spectrum starts with the cosmic rays, or gamma rays, cosmic rays. And then we have these cosmic rays has the highest frequency. So cosmic rays, then we have the X-rays, then we have ultraviolet rays, UV rays, then we have the visible spectrum, then we have the infrared, then we have microwaves, and then radio waves. And the radio waves has the longest wavelength and has the least frequency, and so therefore radio waves are weak. They have lesser energy as compared to cosmic rays, which are very high energy. We know that X-rays also possess high energies. Therefore, it can pass through human tissues, but not solid objects. Therefore, we can take X-ray pictures for diagnosing broken bones. Now this electromagnetic spectrum came about because of electromagnetic wave theory, and there are two major points in electromagnetic wave theory. Those 2 points are: a source emits energy continuously in the form of radiations. That means no change in wavelength or frequency of the emitted radiations, even on increasing the energy. The second point is that these radiations are electromagnetic in nature. But there was failure of the electromagnetic wave theory because it failed to explain two experiments in particular. The first one is the black body radiation, and the second one, the photoelectric effect. Now, by this time, we know that light behaves as waves, but certain features, some of the phenomena such as diffraction and interference can be easily explained by the wave nature of electromagnetic radiation. But some of the observations, like the nature of emission of radiation from hot bodies, that is our black body radiation, ejection of electrons from metal surfaces when radiation strikes, the photoelectric effect, and variation of heat capacity of solids with respect to temperature, line spectrum of hydrogen, those were some of the things which couldn't be explained solely based on the wave nature of light. Therefore, the electromagnetic wave theory had failure. So Planck, but before we go to Planck's quantum theory, let's try to understand what is a black body radiation and photoelectric effect. Now, according to Maxwell, on hitting a body, the intensity should increase. That is, energy radiated per unit area should increase without having any effect on the wavelength or frequency. But whenever we hit an iron rod, it first turns to red, then white, and then becomes blue at a very high temperature. This means that the frequency of emitted radiations is changing. So the variation of intensity shows that with increasing temperature, the wavelength also changes, it varies. That means it emits at a higher frequency if you increase the heat temperature of that body. That is the observation from black body radiation. The photoelectric effect is like whenever radiations with certain minimum frequency strike the surface of a metal, electrons are ejected from the surface of the metal. This is called the photoelectric effect, and the electrons emitted are called the photoelectrons. Now, this two things, the black body radiation and the photoelectric effect, were a hindrance in the progress of the study of light or electromagnetic radiation. So we move on to Planck's quantum theory. Now, this black body radiation was explained on the basis of particle nature of light. Can only be explained on the particle nature of light. Even photoelectric effect can be explained only on the particle nature of light. So now we can see that light behaves both as wave as well as particle. The photoelectric effect is can be explained on something called threshold frequency. Now, what is threshold frequency? For each metal, a certain minimum frequency of light is needed to eject the electrons. That is our threshold frequency. Now, once a metal is irradiated with a particular frequency greater than the threshold frequency, then the electrons gets ejected from the surface of the metal. That is how that is the principle on which solar cells are also based. Now, Max Planck proposed that the amount of energy associated with a quantum of radiation is proportional to the frequency of light. That means the energy is directly proportional to the frequency of light, or energy is equal to h nu, and this h is our Planck's constant. And we also know that the speed of light is related to lambda and nu, frequency. So frequency is equal to c over lambda, and if we substitute here, then energy is nothing but h c over lambda. This is an important relation. These are important relations we need to keep in mind. Now, along with the threshold frequency, there's another thing called the work function. Now, if the energy of the striking photon is given by h nu, and the minimum energy required to eject the electron is h nu naught, the minimum energy, then the work function, or the difference in energy, is given by h nu minus h nu naught. So this is, or h is simply nu minus nu naught. This is also an important relation for us, the work function. Now let's try to solve an example. So this is the question. The threshold frequency is given. We asked to calculate the kinetic energy of an electron emitted when radiation of frequency nu hits the metal. Now we know that kinetic energy is equal to half mv squared, which is nothing but the work function which we just solved, h nu minus nu naught. So if you plug in the values, this is a constant. I think I've already given to you in the printout, the readout. So you plug in those values. So Planck's constant is 6.626 into 10 raised to the power kinetic energy. 6.626 into 10 raised to the power minus negative 34 into nu is 1.1 into 10 raised to the power 15 minus nu naught is 6 into 10 raised to the power 14. So if you solve solve, then you get 3.313 into 10 raised to the power negative 19 joules of energy. That is a kinetic energy. Next, we'll try to look into Niels David Bohr's atomic model. It is based on quantum theory of light. The assumptions that were made by Bohr in his model of atom was that the electrons were revolving around the nucleus in fixed orbits, and while they are revolving, they do not radiate energy. Those were fixed orbits for each of the electrons. That was the first assumption. And another assumption was that the electrons, suppose this is a nucleus, and electrons were revolving around in fixed orbit, so it doesn't radiate energy, so it takes care of the Rutherford's model of atom, and that electrons can jump from its orbit to another higher orbit by absorbing energy, and while after jumping to the higher state, it comes down by emitting the same amount of energy that it has absorbed. So that was what that were the assumptions of Bohr, Niels David Bohr, in his atomic model, and that the energy emitted during these transitions were hc over lambda. But there were some limitations of his theory, Bohr's atomic model, that he couldn't explain the line spectra of atoms containing more than one electron. He also could not explain the presence of two closely spaced lines. In his theory, his theory failed to explain the splitting of spectral lines and magnetic fields, the Zeeman effect, and electric field, the Stark effect, and then the dual nature of matter, like the light behaves both as particle as well as wave, couldn't be explained from his model, from his atomic model. So those were some of the failures or limitations of Bohr's atomic model. Next, we'll discuss the atomic spectra. Now, unlike the spectrum obtained by analyzing the splitting of white light, sunlight, the spectra of atoms are not continuous. They consist of sharp, well-defined lines or bands corresponding to definite frequencies, and the spectra are of two types: emission spectra and absorption spectra. The emission spectra are obtained when the radiation emitted from substances that have absorbed energy, and the absorption spectra is obtained when a continuous electromagnetic radiation, say white light, is allowed to pass through a gas or a solution of some salt, and the transmitted light is analyzed. Then we obtain an absorption spectrum. Now, when hydrogen gas was introduced to an electric discharge tube at low pressure, then the emitted radiation, or the emitted light, it splits into fine lines or sometimes we call as the fringe width. Let me show you. So here, these are fringe widths. The atomic spectra looks like this one, as small sharp lines. And the absorption spectrum, when sunlight was passed through a small slit, sunlight was passed through a small opening slit, sunlight was passed through a slit, through a sodium chloride solution, and that rays were allowed to pass through a prism, then dark bands were observed, or dark lines were observed on a photographic plate. So those were that is an example of absorption spectrum. When the absorption emission spectra of hydrogen is analyzed, we can see that it consists of the Lyman series, the Balmer series, Paschen, Brackett, and Fun series. Even Humphrey series is also included. Now, this series, or the spectral lines of hydrogen atoms, can be calculated on Rydberg by Rydberg equation. 1 by lambda is the wave number, which is equal to r into 1 by n1 squared minus 1 over n2 squared, where n2 is always greater than n1. So the Lyman series falls under the ultraviolet region, the Balmer in the visible region. Paschen, Brackett, and Fun series, they fall in the infrared region. For Lyman series, n1 is equal to 1 and n2 can be 2, 3, and so on. For Balmer series, n1 is 2 and n2 can be 3, 4, and so on. Likewise, for Paschen, n1 is 3, Brackett 4, for Fun, n1 is equal to 5. Let's work out an example. So here is an example. We are asked to calculate the wavelength of a photon. So when the transition is from n2 to n1, so we know that from the Rydberg equation, 1 over lambda, which is the wave number, is equal to r z square. This is the atomic number, z is our atomic number, and 1 over n1 squared minus 1 over n2 squared. So r is the Rydberg constant, r into, and the atomic number of hydrogen is 1, so 1 squared over 1 by 1 squared minus 1 by 2 squared. So 3r over 4, 1 by lambda. So lambda is equal to 4 by 3r. This is our solution. Here are 2 more examples which you can try on your own. If you need any help, you have my number, so you can contact me, or you can leave a comment below. De Broglie wavelength and Heisenberg's uncertainty principle. Now, dual nature of electron. De Broglie, that is, a dual nature of electron was proposed by de Broglie. But before de Broglie, Einstein suggested that light can behave both as a wave as well as particle. That means light has a dual character. In 1924, de Broglie proposed that an electron behaves both as particle and as a wave. This proposed new theory, the wave mechanical theory of matter, was called the wave mechanical theory of matter. And according to this theory, the electrons, protons, and even atom, when in motion, possesses wave properties. So according to de Broglie, the wavelength associated with a particle of mass m moving with a velocity v is given by the relation lambda is equal to h over mv. H is the Planck's constant, m is the mass of the particle. Now this equation has been derived from Planck's equation. Planck told that energy is equal to h nu, or it's equal to hc over lambda, and from Einstein's energy mass relation, energy is equal to mc squared. So if we equate these two equations, mc squared is equal to hc over lambda, and then we end up with lambda is equal to h over mv, or in this case c, just the velocity, speed of light. So this is also another important relation. And Heisenberg suggested that the change in position and change in momentum of a microscopic particle is always greater than or equal to h over 4 pi, which simply suggesting that we cannot simultaneously measure the position or the momentum of a microscopic particle. So here's another example. We are asked to calculate the uncertainty in position. So we know they have given us the accuracy as 2%. So uncertainty in speed is uncertainty in speed is 2%. That is 45 into 2/100, which is equal to 0.9 meters per second. Now we know that uncertainty in position is we know from Heisenberg's uncertainty in position is del x into del p is greater than h by 4 pi. So this change in position is equal to momentum is nothing but this momentum is a mass into acceleration or velocity. Mass doesn't change, so but velocity will change. So we can rewrite the equation as this, and so our uncertainty in position would be greater than or equal to 4 h Planck's constant 4 pi m del v. Now you can let's plug in the values. So our change in position will be greater than or equal to Planck's constant is 6.626 into 10 raised to the power negative 34, and then 4 into 3.14 pi value. Mass is uncertainty in speed or velocity is 0.9 meters per second, and the mass is 40 grams, or we can convert it into kilograms. So our uncertainty in position will be greater than or equal to 1.46 if you calculate it into 10 raised to the power negative 33 meters. So we'll wrap this chapter in with another part